In this video, we're analyzing a rod that is attached to a wall, and it has a cable holding it up, supporting it, and there's something hanging from the end. There's a load of 80 newtons. So we can go ahead and draw the rigid body, free body diagram. Remember, the location of the forces is super important. So we have the 80 Newton force acting at the right end, and then we also have this tension force, and that's acting all the way at the right end as well. And we see there's a 30-degree angle with the horizontal. We know the beam itself has a weight of 28 newtons. At the wall, it's attached right there. And so the wall can be exerting a horizontal force and a vertical force. It makes sense that the wall would be pushing up, and so we're going to call that R sub y. It's the reaction force at the wall, or you can just call it F sub y. The only other horizontal force is T sub x, and that's to the left. So that means our R sub x is going to be to the right. Now we're going to go ahead and pick up to be our positive direction, to the right to be our positive x direction, and counterclockwise to be our positive direction for torque. We get to pick an axis of rotation wherever we want. We could pick it in the middle, on the right end, right here, anywhere that we want. We have three unknowns, and those are listed here, Rx, Ry, and T. If we selected the right end as our axis of rotation, that would be a nice choice, because then the torque due to the tension, T, would be 0, and the torque due to R sub x would be 0, because R sub x is acting directly through that. The line of action of R sub x is going right through this right end, if we pick that to be our axis of rotation. And so then R sub y would be the only unknown in our torque equation. So that would be a great choice. We can also pick right here, which is what most students would probably do, so I'm going to go with that. I encourage you, however, once you've finished watching me try this problem in the video with the left end as the axis of rotation, go ahead and try the right end. Do the problem over with the right end as the axis of rotation and see that you get the same Rx, Ry, and T. All right, with this as the axis of rotation, we can go ahead and sum the torque. Equal to I alpha. It's an equilibrium problem, so the angular acceleration alpha is 0. So Rx and Ry don't create any torque relative to the axis of rotation. We have the 28 Newton force, which is, let's see, the entire rod is 1 meter in length, so 0.5 meters from here to here. And then it's a 90-degree angle when we draw in our lowercase r. It's a 90-degree angle, so sine of 90 is 1. And then we say minus 80 newtons times 1 meter. And again, that's forming a 90-degree angle with the r for that one. The r for that force would go out like that. And then we've only got the tension left, and that's going to create positive torque. Okay, so that's tension, not torque right there. But the torque created by the tension would be T times 1 meter times the sine of 30 degrees, and that's all equal to 0. So we only have one unknown in this equation, so we can go ahead and solve that. I'll leave the algebra to you, but it comes out to 188 newtons, and that's one of our answers. We need to find two more unknowns, and we have two more equations that we can use. We can sum the forces in the x direction, set that equal to max. We can say, all right, well, Rx, all of it acts in the x direction, minus 188 newtons times the cosine of 30 degrees. And that's equal to 0. The acceleration in the x direction is 0. From that, we can get that Rx is equal to 163 newtons. We can then sum the forces in the y direction, set that equal to MAY. So we have RY acting upward, minus 28 newtons, minus 80 newtons, plus 188 newtons, that's T, times the sine of 30 degrees. That's equal to 0. And remember, when I'm doing these three equations, when I sum the torques, it needs to be force times distance, force times distance, force times distance, and including the angle. Remember, these were sine of 90, which is equal to 1 for both of these. But it's torque, torque, and torque. Okay? Here, summation of forces. So it's a force, and oh wait, what's this cosine 30? Remember, that's just so we can find the x component of the tension force. But it's still just a force. Look at the units. It's newtons, and then cosine 30 doesn't have any units. Here we've got a force, a force, a force, a force. Okay, so you got to make sure you keep your forces and your torques separate. Torques go in the torque equation, forces go in the forces equations. R sub y, we can then solve, and it comes out to only 14 newtons. It's a rather small force that's needed to hold that up. We need a much larger horizontal force. Now it did ask for the force of the hinge on the rod. It was singular force. And so we can think of this force, Rx, Ry, we can combine them into a single force. So we've got a large force in this direction, 163 newtons. And then we've got a small force here, 14 newtons upward. And then we draw the hypotenuse, and that's equal to R. And then we've got this angle here, theta. So R squared equals, 163 newtons squared plus 14 newtons squared. So R comes out to be 163 newtons. And interestingly, with the rounding, it turns out that way. And actually, if I kept more digits here, you would see a slight difference. It would be just slightly larger. And so I probably should have done that. I'll let you go back and see that this actually comes out to 162.81 newtons, and then this comes out to 163.4 newtons. So there is a difference. And then we find the angle. The angle is equal to the inverse tangent of 14 newtons over 162.81 newtons. And theta comes out to 4.92 degrees. And so that is our force. Remember, force is a vector, and so if force is a vector, we need to have both the magnitude and the direction. So 163 newtons at an angle 4.92 degrees above horizontal. And don't forget to solve it with the right end of the beam as the axis of rotation. You'll find that works just as well.